Hello and welcome back to the Biochemistry for Health Sciences channel. In the previous video, we talked about reversible and irreversible inhibitors. Unlike irreversible inhibition, reversible inhibition is an important strategy that our body uses to regulate enzyme function. So in today's video, we shall discuss the effect of these reversible inhibitors on two very important enzyme kinetic values, which are Vmax and Km. So let's look at how a reversible inhibitor will affect Vmax and Km and compare that to the same Vmax and Km value without the inhibitor minus the I, which we'll call the control. It is good at this point to remember how an enzyme works. So basically the substrate will combine with the enzyme, so the substrate will enter the active site of the enzyme, and that forms an enzyme substrate complex. This reaction is reversible. The enzyme substrate complex can also therefore break down to give you back the enzyme and substrate. Once the enzyme substrate complex is formed, now the substrate will be converted into the product. This is an irreversible step, and the product will eventually diffuse out of the active site, and that will free up the enzyme once again, and the enzyme can go ahead and pick up another substrate molecule and catalyze another cycle of reaction. Now let's see what happens if we add an inhibitor to the enzyme that is catalyzing a reaction. So when we add an inhibitor, the inhibitor can do one of four things. So in the first case, the inhibitor can bind the free enzyme. So here the inhibitor can bind the free enzyme at the active site of the enzyme. A second possibility is the inhibitor can bind the free enzyme but at an allosteric site, at some other site, not the active site. The third possibility is that the inhibitor binds the enzyme substrate complex. So once the substrate is bound to the enzyme, only then the inhibitor will come and bind to the enzyme substrate complex, and this binding once again will be at an allosteric site. The fourth possibility is that the inhibitor can bind the free enzyme, that is the enzyme without the substrate, at the allosteric site, and the inhibitor can also bind the enzyme substrate complex. Let's see how the binding of the inhibitor affects the Vmax and or the Km of an enzyme catalyzed reaction. Irreversible inhibitors can be divided into three major classes: competitive, uncompetitive, and mixed inhibitor. Now the mixed inhibitors can again be divided into three subclasses: one where the Km is increased, the second where the Km is decreased, and the third non-competitive class where there is no effect on the Km. Let's first look at competitive inhibition. In competitive inhibition, the inhibitor binds the free enzyme. So here we have the inhibitor, here we have the substrate molecule. Both the substrate molecule and the inhibitor molecule are competing for the same site, the same active site of the enzyme. So since there is a competition between the substrate and the inhibitor, we call this kind of inhibition competitive inhibition. Since the inhibitor is competing with the substrate for the active site, this is going to reduce the substrate binding or the substrate affinity to the enzyme, and that is going to lead to an increased Km in the presence of the inhibitor. And we see in the Michaelis-Menten plot, in the presence of inhibitor, the Km is increased. Now the Vmax is not affected because under high substrate concentrations, if we add more and more substrate compared to the inhibitor, the substrate statistically is going to bind simply because there is more substrate compared to the inhibitor, and that substrate binding will bring back the original Vmax. So Km is increased, but the Vmax is not affected in competitive inhibition. In uncompetitive inhibition, the inhibitor binds only the enzyme substrate complex. So the inhibitor will bind at the allosteric site of the enzyme substrate complex. When the inhibitor is bound to the enzyme substrate complex, to give you the ESI, product formation is inhibited, and therefore the Vmax is going to be decreased. So at any time when the inhibitor binds the enzyme substrate to give you ESI, that is going to decrease your Vmax because the ESI will not be converted into product, and that will reduce the maximum velocity. So an uncompetitive inhibitor will decrease the Vmax. Now what about the effect of an uncompetitive inhibitor to the Km? So when the inhibitor binds the ES, that is going to make this reaction go towards this direction because the ES and I are combining to form ESI. So basically the inhibitor is pushing this reaction, this E plus S reaction, in the forward direction towards the ES because the ES is being removed to ESI. And this causes the affinity of the substrate for the enzyme to increase, which means the Km will decrease because a lower Km means a higher affinity of the substrate for the enzyme. So not only will the Vmax decrease in uncompetitive inhibition, the Km will also decrease by the same amount. Okay, so both Km and Vmax are decreased by the same amount. So you can see that here in the Michaelis-Menten curve, in the presence of the uncompetitive inhibitor, the Vmax decreases, while at the same time the Km decreases by the same amount. Now it should be remembered that these enzyme kinetic experiments are done basically in buffers, so very aqueous solutions. This is quite different from what we see in cells. In cells where the enzymes are present, these molecules are very crowded, very crowded, very high concentration of particles, of molecules that are dissolved in the cellular water. So some experiments have been done now instead of buffers, they add what we call crowding agents such as proteins like albumin and other kinds of molecules. And when these experiments are done in crowding agents, what we see sometimes is the decrease in Km is more than the decrease in Vmax. So basically the uncompetitive inhibitor in this case is acting more like an activator. Okay, because activators will decrease the Km, will make this go faster. So we should always remember that a lot of these experiments and information that we have in literature as well as in textbooks are to be used as guidelines, but in reality the situation in the cell can be quite different. Now let's look at mix inhibition. So in mix inhibition, the inhibitor binds the enzyme substrate as well as the free enzyme. Since it binds the enzyme substrate, clearly the Vmax is going to decrease. It doesn't matter what subtype we are talking about. In all these three cases, A, B, C, the Vmax is going to be decreased because the inhibitor is bound to the enzyme substrate complex, and that will stop the formation of the product, and that is going to decrease your Vmax. Now in mix inhibition, the inhibitor also binds, besides the ES, it also binds the enzyme to form an EI complex. So since the inhibitor binds to the enzyme to form EI and binds to the enzyme substrate to form ESI, based on these we can divide mix inhibitors into three types. In the first type, this A, the inhibitor has a stronger affinity for the free enzyme. So this is a stronger reaction. In the second type, in the B type, the inhibitor has a stronger affinity for the enzyme substrate compared to the free enzyme. And in the third case, the non-competitive subclass of mixed inhibition, the inhibitor has equal affinity for the enzyme, equal affinity for the enzyme substrate. So in the first case, in A, since the inhibitor has a stronger affinity for the enzyme, this will look more like a competitive inhibitor, and therefore Km will increase, similar to what we see in competitive inhibition. In the second case, the inhibitor has a stronger affinity for the enzyme substrate, and that's what we see in uncompetitive inhibition. We see a Km decreasing, and that's what we see here in the second subtype of mixed inhibition. And in the third case, in C, what we call non-competitive inhibition, which is very, very common, the inhibitor has an equal affinity for the enzyme substrate as well as the free enzyme. Therefore, the increase in Km and the decrease in Km will cancel each other out, and therefore there is no effect on Km in non-competitive inhibition. So when we look at these subtypes, three subtypes of mixed inhibition, once again you will see in all cases Vmax is decreased. That's because of the formation of ESI in all cases. So the Vmax is always going to decrease in any one of these subtypes. In the first case, the Km is increased, and you can see the Km increases in the presence of inhibitor. In the second case, Km is decreased, and you can see the Km going down in the presence of the inhibitor. And in the third case, there is no effect on the Km. So the Km remains the same. So these are the effects of these reversible inhibitors on the Km and or the Vmax of an enzyme catalyzed reaction. So the effects of these inhibitors on the Michaelis-Menten curve is seen clearly from these diagrams. We can similarly see the effects of these inhibitors on Km as well as Vmax on the Line-Weaver-Burg plot. So for example, in competitive inhibition, only Km increases, so the Vmax remains the same. Remember, this y-intercept is 1 divided by Vmax, so the Vmax is not affected. The x-intercept is minus 1 over Km, and you can see the Km is increased in the presence of inhibitor. So the Km is increased, and remember this is reciprocals. So as we go to lower and lower values, that means the Km is increasing and increasing because these are reciprocals. So just keep that in mind, and you should be able to interpret the Line-Weaver-Burg plots. So in uncompetitive, the Vmax decreases, and you can see the Vmax is decreasing. As its value goes up, that means we are decreasing because once again this is reciprocal. And we see the Km decreasing. So the Km going up, higher values means the Km is decreasing. So in a similar fashion, you should be easily able to interpret all these Line-Weaver-Burg plots for mixed inhibition. Now, suppose we ask the question, how much did the Km and or Vmax get affected in the presence of inhibitor compared to in the absence of the inhibitor? So for example, in competitive inhibition, we said the Km increased compared to the control without the inhibitor, which has its own Km, some Km. In the presence of inhibitor, we have this new Km, and we say this Km is increased. The question is, by how much? And that can be answered by using this factor alpha. So alpha tells us by how much has the Km increased. So alpha is always greater than 1 because we are saying how much has it increased. And alpha is given by this equation. Alpha equals 1 plus I, the inhibitor concentration, divided by the inhibitor constant Ki. So we can calculate alpha if we know I and Ki. So in the presence of a competitive inhibitor, we can see that the Michaelis-Menten equation is slightly modified by putting the factor alpha. So similarly, in an uncompetitive inhibitor, so we see a Vmax is decreased. So how much has the Vmax decreased? We'll use alpha prime. So the Vmax has decreased by a factor of alpha prime. Similarly, how much has Km decreased? Km has decreased by a factor of alpha prime. And alpha prime is again 1 plus the concentration of inhibitor divided by the inhibitor constant for the uncompetitive inhibition. So the Michaelis-Menten equation is modified into this form when we talk about uncompetitive inhibition. Similarly, for mixed inhibition, the Vmax decreases. So the Vmax decreases. So because the inhibitor binds to the enzyme substrate. So we use alpha prime for this. Similarly, we'll use alpha prime for this. So how much has the Vmax decreased? The Vmax has decreased by a factor of alpha prime. Now what about the Km? In this case, Km increases. In this case, Km decreases. For this we use alpha. For this we use alpha prime. So what's the effect on Km? The effect on Km depends on the ratio of alpha divided by alpha prime. Depends who is bigger. Is alpha bigger or alpha prime bigger? So in case of mixed inhibition, the Michaelis-Menten equation becomes this modified form. So let's do a few problems to better understand these concepts. Problem number 1, the linear regression for Lineweaver-Burk plots obtained in the absence, that is the control, and presence of a drug. So here the drug is acting as an inhibitor, and they give you the regression equations for the control, the regression equation for the drug, presence of the drug. What type of inhibition is shown by this drug? Okay, so let's use the equation for the control, y equals 0.17x plus 0.13. So from this equation, we can put x equals 0. We put x equals 0 so that we can get the y-intercept. And the y-intercept comes out to be 0.13. Now the y-intercept is 1 over Vmax. So 1 over Vmax equals 0.13. Therefore, Vmax is 7.7. Now let's find the Km for the control. So once again, we have the control regression equation. Now we get the x-intercept by putting y equals 0 and solve for x. X comes out to be 0.76. That's minus 1 over Km is the x-intercept, which is minus 0.76. Therefore, Km can be worked out, and that comes out to be 1.3. So the Vmax is 7.7, Km is 1.3 for the control without the inhibitor. So let's do the same thing for the enzyme reaction in the presence of the drug. So in the presence of the drug, presence of the inhibitor, now the regression equation is this. Once again, we find out the y-intercept, which is equal to 1 over Vmax, and therefore Vmax is 7.7. So you can see the Vmax in the presence of the drug or the absence of the drug is the same. Now we find out the Km in the presence of the inhibitor. So once again, we have our regression equation in the presence of the drug. Putting y equals 0 will give us the x-intercept. If we work that out, the x-intercept comes out to be minus 0.26, and the x-intercept is minus 1 over Km, and then you can work out Km. Km comes out to be 3.8. So now we compare the values for the control, 7.7 Vmax, 7.7 for the drug in the presence of drug. So the Vmax has not changed. Km for the control 1.3, Km for the enzyme catalyzed reaction in the presence of the drug is 3.8. So Km has increased 3.8 instead of 1.3. Km is increased, but Vmax remains the same. Therefore, this is the features of competitive inhibition. So this drug here is basically working as a competitive inhibitor to this drug, to this enzyme. Problem 2, you're given a diagram. What is the effect of the inhibitor on Vmax and Km, and what type of inhibitor is the drug? So clearly in this diagram, the x-intercept remains the same, so therefore the Km is the same. The y-intercept, however, is changing. You can see in the presence of the drug, the Vmax is decreased. Remember, higher values means lower Vmax. So the Vmax is decreased. So since here we have a Vmax is decreased and we have a Km that remains the same. And this is the features of a non-competitive or a mixed inhibitor. The subtype is a non-competitive mixed inhibitor. Since your Vmax is decreased while your Km remains the same. Problem 3, the following data was obtained for Lineweaver plots. Units of S and V are millimolar and micromole per minute respectively. So here we have our Y and X intercept for the control, Y and X intercept for the in the presence of the drug, in the presence of the enzyme of the inhibitor. Question A, determine Vmax Km. Question B, what type of inhibitor is the drug? Question C, if the inhibitor concentration is 0.2 millimolar, what is the inhibition constant, Ki, for the inhibitor? So as before, we can calculate the Vmax from the y-intercept for the control and the Km from the x-intercept of the control. And similarly, we can find the Vmax for the inhibitor and the Km for the inhibitor. So when we compare these values, we see that what is happening is Vmax is decreased. So Vmax goes from 8,000 to 6,370. Km remains the same. 7.46 millimolar here, 7.46 millimolar here. So once again, this is a non-competitive inhibitor. So the third part, if the inhibitor concentration is 0.2 millimolar, what is the Ki for the inhibitor? So for this part, we will use this relationship. And first we'll calculate alpha. And the alpha can easily be calculated. So that's the factor by which, in this case, the Vmax has decreased. So from 8,000, it went down to 6,370. So 8,000 divided by 6,370. So we see that the Vmax has decreased by 1.26 fold. So alpha here is 1.26. Now, the inhibitor concentration is 0.2 millimolar. We put that in here. And we can then find out the value of Ki. So we plug in these numbers and we get Ki, and Ki comes out to be 0.78 millimolar. Okay, so hopefully this video will help you understand the reversible inhibitors and their effects on Vmax and or Km. We will have more videos on the applications of enzyme kinetics in the near future. Until then, goodbye and have a wonderful day.